Welcome back. We're talking about D-separation, and just to recap a little bit, we looked at in the previous, well, a couple videos ago, we looked at these three little cases here where we had just these three random variables and in these three different configurations of a graphical model, this tail-to-tail relationship at C, the head-to-tail relationship at C, and the head-to-head relationship at C. And then we started defining some things here. So we, of course, defined the usual concept of descendants in a directed graph. And then we reminded ourselves what a path was. A path is a sequence of vertices. So a path from a path between two vertices, say 1 and 4, is a sequence of vertices like 1, 2, 3, 4, such that each vertex between each pair of successive vertices, there is an edge, not necessarily in the direction that we're traveling. And then we defined, so we let G be some arbitrary DAG, and we said, okay, let's let A, B, and C be disjoint subsets. So we haven't used A and B yet, I guess, but C played a role here. So A, B, and C were disjoint subsets of vertices, and their union is not necessarily all of the vertices. And then we defined this concept of a blocked path, and this is a critical concept for D-separation. So a path is blocked. Let's just remind ourselves what this is. A path, not necessarily directed, is blocked if, with respect to C, if it passes through a vertex V such that either the arrows are head to tail or tail to tail. So this was head to tail, this was tail to tail, and that vertex is in the set C. So if either that or this other property B, if they were head to head and the vertex was not in C and none of its descendants were in C. So this one, let's just take a minute to remind ourselves back up here in these three special cases. If we think of actually, A, B, and C here as instead of being subsets of vertices as actually maybe the vertices themselves or the random variables themselves, if we sort of conflate the random variables with their associated vertices, then the path from A to B here, A, C, B would be the path, and it's blocked because it's blocked with respect to C because this is a tail-to-tail relationship, and it passes through C, and of course C is in the set in that case. And for this one, the path from A to B is blocked because it passes through C, and this is a head-to-tail relationship. So so condition A is again satisfied. And for this case, the path from A to B rather, ACB, is also blocked and that's from condition B. Condition B is satisfied because the arrows are head to head and the vertex is not in C. So here the vertex is itself, we're calling it C rather than a set C, but the vertex is not in C, not in the set C, and so this path is blocked because it's a head-to-head relationship at that vertex. So these three examples sort of illustrate that concept, and now we're ready for D-separation. D-separation. So here is the definition. A and B, so we have these three sets here, A, B, and C, disjoint subsets, and I'm using those in this definition. A and B are D-separated by C, by the set of vertices C, if all paths from a vertex, so I could say all paths from A to B, but to be a little more precise, all paths from a vertex of A to a vertex of B, we might call that all paths from A to B, if all such paths are blocked with respect to C. Blocked with respect to C. So I use this WRT for with respect to. So this is the concept of d-separation. A and B, these sets of vertices A and B, are d-separated by C if all paths from a vertex of A to a vertex of B are blocked with respect to C. And here is the theorem. The theorem. Theorem. Let's make a little more room. This is important. This is the d-separation theorem. D-separation. And so d-separation stands for, well, I think it stands for directed separation. D-separation. As opposed to just separation in an undirected graphical model. This is the concept of separation for a directed graphical model. So we know what d-separation is, and now we have a theorem about d-separation, and it is the all-important theorem for conditional independence in directed graphical models. And it says if A and B, again, these are A and B, these subsets, are d-separated by C, then you can probably guess what's coming. A and B are conditionally independent given C. So this is our notation for conditional independence. Note that this does not say if and only if. So they could be conditionally independent and not d-separated. You could construct examples like that, like we did in some earlier video, using maybe some examples from earlier videos. That was sort of the important thing that I wanted to emphasize about graphical models, is that they don't imply that certain random variables are conditionally dependent. They don't imply that they are conditionally dependent. They do imply that they are conditionally independent. So in the same vein, the theorem here says that that if A and B are d-separated by C, then we have this conditional independence property. It does not say that if they are not d-separated by C, that they are not conditionally independent. So just bear that in mind. Remember that important distinction. Okay, so that's the statement of the theorem. Let's put that in a box, because that's a nice theorem, and it's actually it has a very sort of clean, nice proof, but it's not obvious. It's tricky. It's tricky. Okay, so let's stop there, and we'll do some examples of how to apply this theorem in some example graphs. So we'll work through some examples, because it can be a little bit difficult to get your head wrapped around this at first when you first come across this. I know for me it was. For me it was really sort of a challenge to get my head wrapped around, what was going on, and remembering these, this blocked thing is sort of weird. I mean, what is going on with B? This is just kind of strange. All the descendants, what is going on? So I think it would be very instructive to work through a couple of examples and see how this works in action. Okay, so I'll see you back here soon, and we'll do some examples of applying the d-separation theorem to figure out what conditional independence properties hold for certain graphical models. Okay, see you soon.